So once, if the flow is coming from top to down, so the hot plate would be on the top, and the cold plate would be on the, if the temperature of the fluid is like a T reference, which is much smaller than, the hot plate, obviously. So the flow, we can idealize this on a geometry like this, where the top is at the hot temperature and the bottom is the cold temperature, and you have a fluid which comes in between this. So suppose this. So what is the generic problem? So you have a top plate which is at hot wall, and the top and the plate which is at the cold temperature. Cold temperature. I don't know what is happening with this. Yeah. So air typically at T88 Kelvin or 23 degrees centigrade or whatever you can put the reference mark, and flows into the system, and the top wall is heated. So if you have a top wall, then if you want to apply a Bose-Nash model, you must ascertain these two parameters should be much less than 1. So if you want to do this, so let's typically fix this value as 2.1, which is much less than 1. So if you have beta delta T, and if the fluid, since our working fluid is gas, so I can write it as 1 over Tc, where Tc is the cold temperature. So if from here you can say that 2 delta should be 8.4 kilometers, which is fine. So delta T is around 30 degrees centigrades. So typically in a solar collector, the top wall is around 600, 700 degrees centigrades, and the bottom wall is around 300, if you take the reference temperature as 300. So basically you cannot go above 30 degrees centigrade, something like that. So what should be then the model so my problem was that how to simulate these kind of flows. So I started with 2 delta is the channel width. No, I'm saying that if you have 0.1, then it can be this. The length criteria for the Bose-Nash model, it will come out to be that. So if any length which is below this value, it is fine with me. But this is 30 degrees centigrade, so it doesn't happen. Normally at in the solar collectors, it's 100, 200, 300. The temperature difference will be like that. So what we did was, so the model will be, first the model will be compressible flow. So then we expanded everything in terms of gamma m square, and extracted the lower order terms, higher order terms in this, and get another set of equations which we call as the low Mach number equations. This is illustrated by Paolucci. So what you do, you see that, so all the 0th order terms are there, plus pressure is decomposed into a 0th order term and the first order term. So there is slightly additional thing. This goes or not? Yeah. So this is the equation which comes out. So you can see that this continuity equation looks like the similar kind of a continuity equation. But in the momentum term, if you see, there is a P1, which is first order pressure, not the 0th order pressure. Otherwise, everything is same. And in the in the energy equation, you have a dP0 by dt, which is 0 is the 0th order pressure term. And you still have to close the set of equation. So it is interpreted that P0 is nothing like a uniform thermodynamic pressure, and the second order pressure is given, P1 is basically the dynamic pressure, like what we do in our normal kind of scenarios. So my system is an open system where you come in. So P0 is an atmospheric pressure. In a closed system, it will be something like this. So now this literature review, if you see the literature, very few people have simulated for more than, so this value is not coming out. It is 1.0, 1.1, something like that. And Niku has done it for 2, and there is not much work up above that. So this Wangen-Fletcher and Lissanian, these are all compressible flow simulations. So why we want to do this is, if you have use the same compressible flow equations, the first issue will be that the time stop will be very, very small. because you have two types of time scales involved, convection velocity and the acoustic velocity. And the acoustic velocity will not be that important because pressure is not really a function of temperature, or density is really a function of pressure, but it is more a function of temperature. So Buzner's model cannot be applied. So thermophysical properties are also variable. Okay, so we do this and we get this. So the objective was to influence the role and all those things. So we then filtered these equations with using the Favre filter, Favre averaging, and we obtained this equation for simulating. So we considered Cp to be a constant, but K and mu were varied with the help of Sutherland law. So this is our scheme, which everybody kind of I don't know why it is cutting. So you have a filtered field for these are just normal equations. So if you have a filtered field and you have a subgrid component, then you have filtering operation and all those things. So finally, the filtered equation comes out like this, which has 5 equations. Now we did a lot of calculations, and we finally optimized the LES modeling. We used 4 or 5 LES models, and we found that the Whale model was working the best. And for the dynamic Smogensky model, for KT, I used dynamic Smogensky model. People have done with constant Prandtl number also. People have done with it, but I found this giving the best results for my simulation case. So domain was this 465Q. We did 3 types of simulations and validations: isothermal, forced, and mixed convection. And you can see that the results compare very well with the published results. This is with the Kim, where isothermal. This is the isothermal case. Normally came in Moon paper with a very, very small satisfaction, so that we can compare with the RE tau 180 simulations, and you can see that the variation very well matches. So this is for 100. This is for forced convection with RE theta 2. So this is mean velocity, mean temperature, mean in the this U prime. So this is for the mixed convection validation. So you can see that the plume it is coming for because of this internal gravity waves. And then these are the validation parts. So now, so what we try to do is to see that what happens with the stratification, with the temperature difference. What happens when you increase more and more temperature? What happens with that? You see that this is the for 1.01, 2, and 3. So where 3 means like if you have a typically lower temperature is 300, the upper temperature will be 900 degree, 300, 600. Obviously 900 is too large, the radiation effects will come into play, but we have, for the sake of physics, we have ignored that. You can say that as the temperature difference increases, the temperature ratio increases, the profile becomes a slightly asymmetric. You can see that there's a shift towards on the right side, on the hotter side. So you can see over here also, shift becomes more and more apparent in the E. This is energy. This is URMS and VRMS typically scaled with the hot wall temperature. U tau is the hot wall, cold wall. So you can see that there is a shift. But these are not symmetric. For 0, 1 is symmetric. The more you increase the temperature ratio, the asymmetry increases, and the fluctuation increases on the cold side but decreases on the hot side. That is also important. So the fluctuation, temperature fluctuation and velocity fluctuations basically decrease on the hot side. So top side of the channel I'm calling it the hot side, and the lower side of the channel calling it the cold side channel. So as you increase for 395, read out 395, the similar results come into play. So here also you see the air symmetry. You can see that the symmetry shifted towards, and you can see the U prime W prime correlation also. So slight decrease in U prime W prime. So you can see the turbulence shear Reynolds stress is also going to decrease as you increase the temperature fluctuations. So I don't know why it is going like this. So this is our RE tau 180 and 3, 1 and 3. So top wall is a cold wall. This is for the hot wall for the RE tau 180. So these are streaks, velocity streaks. You can see that in the D part, which is at 3, RE tau 3. So there's very, very less amount of streaks or no amount of streak was present. So So we have also done for the Ra theta 5. You can see there are very, very long structures of H value which comes into play. So you can also you can see that there's a shear rate we have calculated, which is production term divided by the dissipation term, and as can be seen that as the production term becomes greater than 1, if this S shear rate is greater than 1, there is a chances of the burst. But you can see that for the Ra theta 5, the burst, there is a very, very small value of increase in value is greater than 1. So you see that there is so we thought about how to more get into the physics of this. So we did a POD of that, of these flows, and you see that, so POD is a pretty standard technique which everybody knows, so I'm not going into the basics of POD, but I will just give the results of this. So as you see that for RE 1.01, the amount of snaps which was required was still 3,000, more than 3,000. So 0.275. So this is the convergence part. But if you see that for RE theta 3, it's slightly lesser, 0.3841 and 0.40. So around 100,000, 1,500, these snaps, these amounts, the flow converged. So we can take 3,000 snaps. So you can see that. So cumulative energy ratio. And as the cumulative energy ratio, so you can, so what happens with this, as the thermal stratification increases, the relative energy content of the lower modes becomes lesser and lesser, so larger and larger. So this normally, if you have a periodic flow, so the most energetic mode will be the first mode, So as the turbulence, if the turbulence is large, that means there are a lot of wave numbers are present. If the turbulence increases, there are a lot of more wave numbers are present. So the energy is distributed into many, many scales. So more wave numbers are present. So if the larger the number of snaps used, the larger is the more is the turbulence. Try to correlate with that. So that is what we found, and we found that the energy eigenvalue spectra gives that the energy content will be like more the modes and lesser than this. So the energy fraction, if we try to calculate the energy fraction for R theta 1 and 3, the first mode contains about the energy fraction is 2.9%, and in the first mode of the the energy fraction is around 6.2%. So you can see that 3%, 2% energy is basically in the first mode and second mode, and you can see that not much deviation is there. So for the first 20 modes I have given over here, and you can see that still 10 modes, around 1% energy is there, and all of the energy is distributed into very, very fine scales. But if you consider the same value over here, so it is around the 20th mode has around 0.06%, 0.6% of the fraction of that. So the faster convergence is basically attributed to probably the relaminarization or something like that. To put the and the lower modes correspond to the larger scales, and this is the way I have discussed. So if total energy is 21%, so 20 modes, first 20 modes has only 21% energy. But for the R theta 3, first 20 modes has 29.5% of energy. So the first mode for the non-isothermal case, the first mode has 3%, while as the third mode has 6.2%. Similarly, things are there. So now what we try to do is this first mode. If I take only mode 1, which is this kind of, so if I try to reconstruct with only mode 1, so I get a long structures like this, which is the first most energetic mode. If I try to do another reconstruction with only the second mode, so I get more structures over here, elongated structures, which I call it as the roll modes, which is followed from the Weber's paper of minimal channel flow. So that you can see that 2% consists of 2.2% of energy, and for the isothermal and non-isothermal case, the reconstruction shows that you have a streamwise direction, and this is the roll modes. Now, if I consider the similar temperature, so Weber's papers was only for isothermal case, so they did not consider for the this type of temperature cases. And so the first mode and the first plus second mode, you can see that the isothermal cases are there. So these we call as the semi-roll modes. So they are elongated structures, but slight breakages are there. They are elongated structures, but their slight breakages are there. If you consider for the third mode, you see that these type structures are slightly tilted. So what I get from this is, and we call these as propagating modes. So if I try to calculate energy in these modes, so one mode and the other mode and the third mode, so we can calculate from this, where A's are basically the coefficients, and PM is like a probability for this portion of energy in this mode. The energy for all the KLM modes are basically given by the ET. And if you see this structure for 1.01 is this and 3 is this, you can see that there are two large peaks, so probably two large and one small. So there some event has occurred. I do not know about what event. I tried to do this, but I'm still facing difficulty in collaborating each other. And with ET over this, but if I try to calculate the entropy, so there's an entropy changes over here, another entropy changes over here, but smaller entropy. So you can see that the distribution of entropy is nearly similar in these large modes. So in this at higher RE tau 3. So there's a smaller the one. So the smaller the range of RE entropy, the larger is the lesser is the turbulence. So I try to figure out what happened. So I try to plot between T plus and 917 1500, where the peak was there, and I saw that there is a slight elongated type of structures, tilted elongated structures. So probably this mode is what is causing relaminarization because it is interacting. I'm still working on it, so we have not. I'm not very sure that exactly why this comes out. But what I think is that there's some interplay between this propagating mode and the roll modes, which basically inhibits turbulence in the hot part of the channel. So that is what I wanted to contribute. So thank you. If you have any questions, please.
Questions? Mahendra.
This is not boosted.
So, what about the flux, heat flux? Does it decrease when you go up?
Yeah.
Or do you have that heat flux thing?
Yeah, we have. Well, I'm not shown, but we have. The heat flux decreases as you go to the top. Okay. So if you have, I have done for the mixed convection case, and if you have gravity, if you have, right now this is for the forced convection results. Okay. So if you have gravity also, so then there is a barrier over there. That is what the internal gravity based thermocline. And there also there is that also causes this.
Why can't this be implemented by just taking conservative form and then writing the state equation and do it? You need to do this way only?
No. But that can be done. For people, people have done this with the conservative form. But then your delta T cannot be more larger than 300, 30 degrees. Or basically, if you take conservative form and you write it like this, you take the variation of those. That is what I'm saying. But those you will apply Buzner's model or not? So you will take only compressible flow, full compressible flow equation. Yeah, that people have done with this. But the problem with this is that it limits the time step. So if you have a slightly large RE theta, that is people have done it for 2, RE theta 2. So if you have more than that, so the time scale will be, because there is a limit, because there are 2 time scales involved. One is the convection velocity time scale and the acoustic time scale. Pressure will cause basically the smallest part. And so that is why we filtered. And there is a paper by Huang who said that if you take in like a full compressible flow equation, if you solve, then it is not, what was the word which was used? But that gets, fluctuating component gets disturbed because of this acoustics.
No more questions. Let's thank the speaker.